Welcome to the Mad Dog Institute of Metal Detecting and Hole Digging. Today we're going to be talking about how DDD coils work and try to understand it and see if that understanding can be applied to better use of that coil. What you see here is a graphic demonstration of what a double D coil looks like, and the graphic comes to us compliments of Metal Detecting World site.com. It would lead you to believe that the green areas are the areas where targets are actually detected. We're going to see if this is actually true or not. In this graphic, it depicts the magnetic induction surrounding a wire carrying a current. This is exactly what happens in our coils. And each one of those circles around that wire, the intensity of the magnetic field is constant along that entire circle. But the magnitude of B, which is the strength of that, decreases as the inverse of the radius or the distance to the wire. What you see here is a depiction of two wires carrying in opposite directions. The green line represents a constant magnetic strength of magnitude B. If both wires are turned on at the same time, then the green magnetic fields are distorted as represented by the black lines. All these lines have a constant magnetic strength of B. These distortions are exactly what is occurring in a detector coil. Note, the magnetic fields herniate out of both the top and bottom of the coil. This chart is quite busy and depicts the magnetic fields generated in a double D coil. The two coils in a double D coil cannot operate simultaneously and therefore alternate on and off at a very high frequency. The gray area in the center represents where the two coil fields overlap. It appears that the audio volumes reported by the two fields are added together to yield a stronger audio signal. The effect is represented by the graph in red that depicts this doubling of audio volume. Point B is the deepest depth for additive volume reporting, while point A represents where the max detection depth actually occurs, although the audio volume at B will be significantly higher than at A. Let's talk about what we observed and can deduce from the bench test we just performed. First of all, audio signals are generated anytime a target upsets a coil's magnetic field if within the sensitivity setting. Upsets to the magnetic field are rate dependent. A stationary target will not generate an audible sound. Audio responses are generated when the target accelerates in a constant magnetic field. Audio responses are also generated when targets traverse multiple magnetic gradients. The stronger the magnetic field that is disrupted, the larger the audio volume reported. Also, the magnetic fields are strongest the closer the target approaches the coil winding, not the ground plane of the coil. The detector appears to add the audio volumes reported in both coils where they overlap. What are some lessons that we can learn from what we have observed? First of all, a shallow target traversing an outer coil can sound nearly identical as a target traversing the coil center line. A shallow target will present as 3 or 4 distinct beeps in a single pass. Shallow targets can often give a false pinpoint when under the coil's outer boundary or perimeter. A DDCoil's characteristics are most pronounced in large coils, but they are common to all DDCoils regardless of size. Let's talk about some tips that we can formulate from what we've seen. If the target is shallow and you lift the coil off the ground 3 to 4 inches while continuing to pinpoint, the audio will drop off rapidly or completely disappear. That means the target is somewhere under the coil's outer boundary and not down the center line. The audio volume and frequency while pinpointing when the target is under a coil outer boundary is often less than when the target is under the center line. You need to learn to recognize the difference. A 4 or 3 beep response indicates a shallow target. The target is under the center beeps. If your sweep is too fast, you may miss these beep distinctions. There are problems that can occur while pinpointing shallow targets with DDD coils. First of all, pinpointing can occur on a coil's outer boundary or perimeter, as well as its center line. The only way to check for this is by doing a coil liftoff 3 to 4 inches. And what I mean by that is, if you're over it and you think it's a good target, just lift it off 3 or 4 inches, and if it rapidly disappears, it's probably under the boundary. If the target fades away, then your target is somewhere under the coil's perimeter. Look there. This issue often results in digging empty holes. It's more pronounced the larger the coil is. So let's look at what is happening using a visual aid. Let's take a look at some different situations that you can run into when you're trying to pinpoint a shallow target with a DD coil. And this particular thing, the center represents the actual location of the target. In this case, it'd be a small coin. And we come in and we get a beep, 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 beep while we're oscillating the coil. And we get a nice real beep, 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 beep. And then we'll switch to pinpoint mode and it goes. So we think we're on the target there, and then we'll toe off. And so the target is here, but now we think it is right here. And you can go through many different iterations of this, and what you wind up with plots along here. So these plots represent all the different possibilities, depending on where you approach this coin on this thing, as to where it will report the erroneous position. So these curves are where it can potentially report an erroneous position of the coin, when in fact the coin is right here. Understanding the magnetic field patterns in a double D coil, as well as the target responses, can significantly improve the efficiency of your detecting. I hope you enjoyed this and found it worthwhile.